Hi students, this is Madhu Dharmapuri, and in this video lecture I am going to teach you what is magnetic flux. Very important concept in magnetism, very much useful in electromagnetic induction. We will see what is electromagnetic induction in the next lecture, but very useful concept. Magnetic flux, which is represented with pi b. Right? So in the previous video lecture, we have discussed about magnetic field lines. Right? So magnetic flux is defined using magnetic field lines. But we need a surface. Right? Surface can be two-dimensional or three-dimensional. That means open surface, that is two-dimensional, or closed surface, three-dimensional. Right? Magnetic field can be uniform, that is constant magnetic field, or it can be non-uniform, variable magnetic field. Whatever it may be, you can define magnetic flux. The magnetic flux is nothing but the total number of magnetic field lines passing through surface normally. See, if you place one surface in the magnetic field, then see how many magnetic field lines are passing through it normally. That is magnetic flux. See, let me take for example, if this is a surface, rectangular in shape, placed in magnetic field. See, for example, magnetic field direction is towards my left, and imagine that these my four fingers represent the magnetic field lines. Okay, so if I place a surface in the magnetic field in this way, then the magnetic field lines are passing through this surface normally, you can see, normally. Then the magnetic flux here is the number of magnetic field lines passing through this surface normally is 4. For example, if 4 lines are passing through it. But if I place the surface in this way and magnetic field direction is towards my left, towards the fingers direction, and if you see in this case, the magnetic field lines are not passing through this surface normally. See, normal means this side towards you in the present case, but the magnetic field lines are passing from right to left, from my right to left. So in this case, there is no magnetic flux. So magnetic flux means number of magnetic field lines passing normally through the surface placed in the magnetic field. Right? So it is a scalar quantity which has units Weber or Tesla meter square. Tesla meter square. To make you understand more clear, let us consider one surface of any arbitrary shape. It can be 2D surface, it can be 3D surface. See, I have talked more about these 2D surfaces, 3D surfaces when I have discussed electric flux, electrostatics video lecture number 4. There I was discussing about area vector, how area is direction, area vector direction is considered for 2D surfaces and 3D surfaces. If you have not watched that video lecture, I do suggest you to watch that. I will provide the link of that video lecture in the description column of this video lecture. Very useful. See, we all know that the area is a vector quantity. Area of any surface is a vector quantity, and it should have direction, and the direction of that area is always perpendicular to the surface. Always perpendicular to the surface. For example, if this is a surface, the area of this will be always perpendicular to it. That means this side or this side, right? So this is a 2D surface, open surface. So 2D surfaces or open surfaces will have two outwards normals, and outward normal is generally taken as area vector direction. And whereas a closed surface is like a sphere, it can be cube, it can be anything which is closed, the surface is closed. The area vector is always perpendicular to the surface. Wherever you see, we generally consider small area elements on the closed surfaces, and on those small area elements that we have considered, the area vector is always perpendicular to that small surface that we have considered. So if I look from here, the area vector direction is here at this particular area, and here it will be like this, here it will be like this, here it will be like this. So outward normal. Here you have no another direction for area, just like for this 2D surfaces, outward normals are two sides. One is this way and the other one is this way, right? But for 3D or closed surfaces, only one outward normal, which is considered as area vector direction. Remember, area is a vector, and magnetic flux is linked to the area of the surface placed in the magnetic field. This is the reason I am talking more about area, and I am suggesting you to watch that video. Okay, so let us consider one surface placed in magnetic field, right? And if I want to find out magnetic flux passing through that surface, linked to that area of that surface, then what should I do is, I should consider one small area element on that surface whose direction is always, as I have told you, that outward normal. So if this is the area element that I have considered, its outwards normal direction is this way, and let us say magnetic field direction is this way, and the angle between magnetic field and the area vector direction of that small area element is theta. Then the flux linked to this small area element whose magnitude is ds, the area magnitude, will be d pi b equal to b bar dot ds. So this d pi b is the flux linked to the small area element that we have considered here. And if I want total magnetic flux passing through this entire surface, then I just have to consider small area elements in each and every place throughout this surface, and find out magnetic flux passing through each and area element, and adding all of them. See, depending on the magnetic field magnitude, we will have a different magnetic flux passing through different small area elements if a magnetic field is not constant. If magnetic field is constant, then at each and every area element that we have considered on the surface, and the d pi b will be same if b is same. If all the area elements are having same magnitude, right? So that is a special case. But in general, we divide the surface into small area elements and finding out the magnetic flux passing through that small area element, and adding all the fluxes passing through small area elements will give you the total magnetic flux passing through the surface. That is adding up means nothing but integration. So the total flux passing through this surface will be integration of d pi b. It is a sum of the individual fluxes passing through each small area element with area ds. That is integral d pi b. So the general formula for finding magnetic flux will be this, because d pi b is b bar dot ds bar. So we have this integral surface b bar dot ds is a general formula, right? And b bar here is magnetic field at small area element ds at this particular place. If it is uniform everywhere, b will be same, but we don't know. We are discussing the general situation, right? So ds bar is the vector perpendicular to the surface of small element with magnitude equal to area ds. So it's a area vector basically with magnitude ds of this small element. Okay, and this formula is useful for two-dimensional surface, that is open surface, three-dimensional surface, that is closed surface, and placed in uniform as well as non-uniform magnetic field. See, even if B is changing or B is constant, for open surfaces, closed surfaces placed in uniform or non-uniform magnetic fields, this formula is useful. This is a general formula. Okay, pi b equal to integral b dot ds. And remember, this is a scalar quantity. It's a scalar quantity. Okay, see this. And most important point here is this one. The number of magnetic field lines passing normally through the surface. These lines are only considered for finding magnetic flux. Right? The magnetic flux is equal to number of magnetic field lines passing through the surface normally. Remember this. Okay. So from this general formula, let us see one special case, that is, if a two-dimensional surface, that is open surface, placed in uniform magnetic field, that is B is equal to constant. One special case. If open surface or two-dimensional surface placed in uniform magnetic field, that means everywhere B is constant, then how this flux formula will change, and in what factors, in what way it is depending on certain factors. Okay, that we will see. So this is a general formula. So from this only I'm going to take a special case. If let me take out this also. One special case. If an open surface that is two-dimensional of area A is placed in uniform magnetic field, uniform magnetic field B bar. That means B is constant. Okay, B is constant. That means here B is constant. Everywhere magnetic field magnitude is same and direction is same. okay, in a certain region. So from this, what we can write? So pi b is equal to, right? So integral s b ds cos theta, which is equal to, b is constant, so b cos theta is also constant, b cos theta integral ds, and which is equal to b cos theta, and say b cos theta into a, which is ba cos theta, which is b bar dot a bar, right? So here integral ds is equal to a, the surface area. Okay, so how does this look like, the picture, for example? So if this is magnetic field direction, see, uniform magnetic field means the magnetic field lines are parallel, equidistant and straight lines, and in that I am placing a 2D surface. So this is like you can say this, is my area vector. So this is here, now it is A, and this is B, and this is theta. So this is how a 2D surface is placed in uniform magnetic field with area A. So in that case, we get this formula. The magnetic flux passing through a surface with area A placed in uniform magnetic field B bar is equal to pi b equal to b bar dot a bar. And from this, I can clearly write that pi b is proportional to b. You can see this. Pi b is proportional to b, and pi b is proportional to a, and pi b is proportional to cos theta. See, if magnetic field strength is increased, then flux will increase, flux passing through this will increase. If area of the surface placed in the magnetic field is increased, then magnetic flux passing through that surface will increase. If the angle, if cos theta, cosine of the angle between magnetic field and area vector is increased, then flux will increase. So these are the factors that affect magnetic flux passing through the surface. So it depends on B, it depends on A, and it depends on the angle between B and A. It's a very special case. So open surface means something which is in two dimensions, just like this, or circle, whatever. Okay. Now we will see how this B and A and cos theta will affect pi b, because we know that pi b is proportional to B, proportional to A, and proportional to cos theta. Right? We will just see in detail how this is going to affect with increase or with change in B, A, and cos theta. Okay, so let us see that. So let me write the formula here. If an open surface of area A is placed in uniform magnetic field. Okay, so what is the formula? Pi b equal to BA cos theta, which is equal to B bar dot A bar. So this is the formula that we have, right? And pi b proportional to B, pi b proportional to A, and pi b proportional to cos theta. These are the things, right? So first we will see pi b increases if B increases. The up arrow mark represents increase. Pi b increases if B increases. How it is? Let us see. Right? So let me take the magnetic field in this direction. Uniform magnetic field. See, okay. So this is magnetic field direction, and I am placing one area with this is area vector direction. Okay. So angle with whatever may be the angle. Okay, I'm just keeping it fixed. Okay, and I will take another case where magnetic field is increased now. See, whenever the magnetic field lines are closer, then the magnetic field strength is more, the stronger the magnetic field. Remember. So here the magnetic field is now increased because the magnetic field lines are now closer to each other compared to this. And now I am taking the same surface of same area placed in this magnetic field. Same surface of same area. Okay, so same area, same surface. Remember, same area, same surface. Okay, surface is not changed, only magnetic field is changed. Okay, then see how many magnetic flux lines are passing through it. 1, 2, 3, 4, 5, 6, 7. Here flux is 7. Here you see flux is only 2. Two Weber, 7 Weber. You can see. See, magnetic field is now here is weaker. Magnetic field is now stronger. The magnetic flux will increase. The number of magnetic field lines passing through the surface are now more. See, it's very, very simple. See, for example, I have a small surface. Like this placed in the magnetic field. Magnetic field direction is this way towards my left, right? And if my magnetic field is in this way, magnetic field direction lines are in this way. See, you can see only two lines are crossing this surface. Only two, right? Now, if my magnetic field lines are closer to each other like this, now 4 lines are passing through it with the same surface. The magnetic flux is increased, right? And the second case, that pi b proportional to A, pi b increases if area increased. If area increases, pi b increases. Means what? It's very, very simple, right? So let me draw it. So here I am taking magnetic field constant for this case. This is the magnetic field direction. Okay, and the area element now I am taking a smaller one. with the direction of area this way, right? And here if you see, flux is 2. Only 2 magnetic field lines are passing through this surface. Okay, now what I will do, the area of the surface is now increased with the same magnetic field. Okay, magnetic field is now not changed. Magnetic field is not changed. Only area of the surface is now increased. You can see this is the area, for example, and this is B. And how many magnetic field lines now? 1, 2, 3, 4. You can say phi B is equal to 4 Weber. It's very simple. See, there are 4 magnetic field lines, for example, here. I have taken one small surface like this. My hand is one surface, open surface. Okay, so magnetic flux is now 4, right? So instead of this surface, if I take this surface, instead of these 4, the other lines are also passing through this, which I am not able to show you actually. See, for example, there are 10 magnetic field lines in this region, in 10, right? And out of those 10, only 4 are passing through this hand because of the size, and the other 6 are not passing through this surface. They are going either upside or downside, right? But if I increase the area, the remaining 6 are also passing through this surface because of the big size, right? Very simple. So area increased, the magnetic field lines passing through the surface increased. So here it is 2 Weber, and here it is 4 Weber. Right? Okay. Now we will see the third case, that is phi B increases if cos theta increases. If cos theta increases. It's very simple. Right? What is cos 0? Cos 0 is 1. What is cos 90? 0. Right? That means cos 0 is more than cos 90. Right? So let us see that. So first thing, with the same magnetic field, I am doing. Right? So this is magnetic field direction. Right? And surface is also same, but I am going to change the angle between the area vector and magnetic field. Okay, so here if I take the surface like this, right, here the area vector is this side, here theta is equal to 90 degrees, so B is perpendicular to A. Area vector here is this way. I am not able to show you that. Perpendicular, see, the surface is placed like this. Surface is placed like this, so area vector is this way and magnetic field direction is that way. So B is perpendicular to A. So this is pi B is equal to 0 minimum, right? So if I have another situation where the field magnetic field is same, so I am not changing that. Magnetic field is same, but only thing that I am doing is I am rotating the surface with the same magnitude. I am just rotating the surface. Okay. Let us say this area is this way. Right? So here let us say theta is 0. So B is parallel to A. So pi B will be how much? Pi B here will be equal to BA, which is maximum. Here it was minimum. So you can see here cos theta is 0, here cos theta is 1. As cos theta increased, pi B is increased. That means flux is depending on the angle between B and A. Angle between B and A. So this is how the magnetic flux is going to change if certain things are changed, like magnetic field increased, flux increased, area increased, flux increased, cos theta is increased, flux increased. So basically it depends on B, it depends on A, it depends on angle between B and A. Very, very important case. Right? So now we will see another case. If a closed surface is placed in magnetic field, it can be uniform, it can be non-uniform, it can be anything. Magnetic flux passing through closed surface, that is 3D, placed in magnetic field is pi B equal to B bar dot ds bar. So this is the formula. This represents the closed surface. B bar dot ds bar. So it is like consider a sphere. See, this is not a circle, this is a sphere. Okay, so sphere, not circle. Okay, and let us say the magnetic field is in this way. So this is the magnetic field direction, right? So for this, if you consider a small area element at this particular place and at this particular place, and similarly another place, wherever, at this particular place and at this particular place, right? So if you take this, the magnetic field the area vector direction for this is this side, and for this is this side, right? So for this is this side, and for this is this side. And if you see, if this is 1, this is 2, this is 3, and this is 4, right? So here d pi d is, you can say, it is B bar is that side and ds bar is this side. So 180 degrees, almost more than 90 degrees. So it will be negative. So here is also d pi b negative. Here it will be d pi b positive for this one, and for this fourth one also it is positive. For this and this, right? So this is for 1, this is for 2, this is for 3, this is for 4, right? What we can conclude from this? If theta is less than 90, flux is positive, right? So the second thing, if theta is greater than 90, see here it is greater than 90, 180 almost, flux is negative. Flux here is magnetic flux. Okay. Flux is negative. So here theta is greater than 90. This side. See, B is that side and ds is this side. But here 2 and 4, B and ds in the same direction, almost theta 0. Right? So theta less than 90, magnetic flux is positive. Theta greater than 90, magnetic flux is negative. So from this, what we can write is outwards flux, outwards magnetic flux is positive. Outwards means that side, it is going out, positive, right? And inwards magnetic flux, see the magnetic field lines are entering this from this side and leaving from that side. Okay, so inwards magnetic flux is negative, because magnetic flux is a scalar quantity. It can be positive, it can be negative. The magnetic flux is positive if magnetic field lines are leaving the surface, and magnetic flux is negative if magnetic field lines are entering the surface. See, it is just like this. See, magnetic field lines are entering from this side. So magnetic field direction is this way. Right? So at this particular side, the flux is entering. The theta is greater than 90. So flux is negative, inward flux. And these magnetic field lines are coming out of this surface. It is a closed surface. They are entering into it and coming out of it. So here, the magnetic field direction is this way and area vector direction is this way for this side. Because area vector is always a perpendicular outward normal. But here it is the area vector is this way. Magnetic field direction is this way. So on this side, area vector is this way. And on this side, area vector is along the magnetic field direction. So this is the reason the theta is less than 90 for this case. Right? So magnetic flux is positive if magnetic field lines are leaving the surface. Magnetic flux is negative if magnetic field lines are entering the surface. So inward flux negative, outward flux positive. Okay, so this is the formula for magnetic flux passing through the closed surface, and this represents that closed surface, this circle. Okay, so hope you have understood about magnetic flux. If you have any doubts regarding this lecture, you can put your doubts under the comment section. Thank you very much.